Okay, given a piecewise function, we want to sketch a graph. Number one, we want to indicate on the x-axis the boundaries defined by the intervals on each piece of the domain. Number two, for each piece of the domain, we're going to graph on that interval using the corresponding equation pertaining to that piece. Do not graph two functions over one interval because it would violate the criteria of a function. So for example 13, what we want to do is we want to be able to graph a piecewise function. We're going to sketch a graph of the function where f of x is equal to x squared if x is less than or equal to 1, f of x is equal to 3 if x is in between 1 and 2 including 2, and f of x is going to equal x if x is greater than 2. So let's take a look here. What do we notice? Well, we do notice that there's something here that we can see that there is a restriction. X is less than or equal to 1 when we graph x squared. Now, we want to use our toolkit functions to refer to just so that we remember. So remember that this x squared represents a quadratic function here. So this is what your quadratic function looks like. Okay, then what we have is f of x is equal to 3. And that has a restriction which goes from 1 to 2, and it's including that 2. Now, this is a constant function because this is a constant. And so therefore, now you're going to see what the graph looks like for a constant function. Okay, and then the last one we have f of x which is equal to x. And therefore, the restriction on that is that x is greater than 2. And that is the identity function. So the identity function is going to look something like this. So you want to refer to your toolkits when you're graphing these. And now what we're going to do is we're going to graph each one of these according to its domain. So each of the component functions is from our library of toolkit functions, so we know their shapes. We can imagine graphing each function and then limiting the graph to the indicated domain. At the endpoints of the domain, we draw open circles to indicate where the endpoint is not included because of a less than or greater than inequality. We draw a closed circle when the endpoint is included because of a less than or equal to or greater than or equal to inequality. So let's take a look at our example, our first one. Okay, so our first example, okay, is our x squared according to this restriction. So we have a parabola where x has to be less than or equal to 1. So here's our parabola, and then it's going to stop when x is 1 and we have a closed dot. So therefore a closed dot stops here and it doesn't continue. So this is our first piece of that piecewise function. Our next one is that we have the constant function, and that is a line that's going to go through the y-axis at 3. Now that line has a restriction. So that line tells us that that number has to be in between 1 and including 2. So there's 1 and there is 2. But if you notice at 1, it's an open circle because it says less than. And then it's less than or equal to, it has a closed circle here. So therefore, there is the second piece of the graph. So there's our first piece, our second piece, and there is our first piece. Now our last piece is the identity function when it is equal to x. But here the restriction is telling us that for x is greater than 2, but we cannot include 2. So here's the value of 2, but you have an open circle here, okay, and then it continues up according to the graph. So that means that it's going to be greater than 2. So now that we have sketched each piece individually, we combine them in the same coordinate plane. So now we have all of this in the same plane. We have, here is our 3 pieces to generate our piecewise graphic function. Now, can more than one formula from a piecewise function be applied to a value in a domain? Well, no, because each value corresponds to one equation in a piecewise formula.